Hello and welcome to this presentation. My name is Sara Dionísio António from the University of Twente, and in this presentation I will present my research, followed by some preliminary first results of a large-scale laboratory experiment on sediment transport in the swash zone. As you all may know, the swash zone is a highly dynamic part of the beach where the waves arrive pushing the sediment up and down the beach slope. Due to its complexity, the processes involved on the sediment transport in this region, such as contribution of wave-swash interactions, advection, and others, are not fully understood. This leads to problems on modeling coastal sediment transport, in which models tend to simplify such processes and neglecting the importance of the transport in the swash zone. A way to obtain such knowledge is through laboratory experiments, where, as opposed to field experiments, wave and beach conditions can be controlled and repeated. Therefore, the overall aim of this project is to observe and quantify the cross-shore sand transport, in particular, how intra-swash processes determine sand transport rates, and ultimately translate this knowledge into a practical and numerical model. If you are interested in knowing more about numerical modeling in the swash, you can watch the presentation of Joost Kranenborg. In order to achieve such goals, large-scale laboratory experiments were conducted with a variety of beach and wave conditions. The experiments were divided in two main experimental campaigns. The first one with a steeper beach slope of 1 in 15 in order to represent the beach in a more reflective state. The slope was also previously done by other large-scale experiments. In the second campaign, the experiments were done on a gentler slope of 1 in 25 in order to represent the beach in a more dissipative state. Large-scale experiments on the swash zone were never done in such a gentle slope. In both slopes, series of irregular waves were done in order to quantify the sand transport rates, and equivalent bichromatic waves were done in order to study the sand transport processes by means of assemblage average of repeated wave motions. The experiments were carried out on the CM large-scale flume at the Universitat Politécnica de Catalunya in Barcelona. Several instruments were deployed along the flume, with the majority of instruments concentrated around the limit between surf and swash zone, in order to have the highest possible resolution of bed level, both bed load and suspended sand concentrations, water level, and flow velocities. As you can see in the picture, the instrumentation were deployed on the side of the flume as close as possible of the profiler in the middle. Besides, there was a movable set of instrumentation to record the wave motions around the main bar, as you can see in the yellow card in the video. Also, parallel dividers were added to minimize the effect of beach asymmetries. For the continuity of this presentation, I will present some preliminary results from the Irregular wave series. This series in both slopes was done by a sequential erosive waves with increasing energy with an interruption of lower energy accretive wave. The green, yellow, and red correspond to erosive waves with increasing energy, and the blue corresponds to the accretive wave with low energy. The colors will remain the same for the next slides. Both experiments started on a handmade 1 in 15 and 1 in 25 slope, followed by a short duration benchmark erosive wave with lower energy. In these plots, we can see the morphologic evolution of the beach. In the left plot, you can see the profiles at the end of each wave condition, and in the right, the time-stacked evolution in which the color represents the difference between the present profile at a given time and the initial bed level. You can see in black the shoreline, the main bar represented by black dots, and the circles represent the secondary bar. As you can see, the increase of energy led to the generation and growth of the main and secondary bar, while progressively migrated offshore. Furthermore, we can see the retreat of the shoreline. During the low energy accretive wave, the main bar migrated onshore while slowly decreasing in height. Also, we can see the outer swash and the secondary trough becomes progressively deeper, and the wide berm is generated around after 6 hours into the accretive wave. When we look at the morphologic evolution of the beach on the 1 in 25 slope, we can see that the development of the beach profiles were significantly softer than in 1 in 15 slope, with differences between the studied and the initial profile about half of what you see in 1 in 15. Also, as opposite of 1 in 15 case, in 1 in 25 the main bar developed at a much slower rate, only being visible by the end of the most energetic wave, at a more offshore location, around 6 meters further offshore than in the steeper slope. Also, no secondary bar was generated in 1 in 25. We can also see that the amount of small perturbations in the bed is higher in the gentler slope due to the waves breaking along a wider area. When looking at the low-energy accretive wave, we can see that, in comparison with 1 in 15, the generated main bar, instead of migrating onshore, just slowly flatten out and remains around the same location, followed by erosion in the trough. The sediment is transported onshore and accumulated in the shore, generating a high berm. Now we can have a closer look at the shoreline evolution throughout the series. In this plot we have the shoreline location on the y-axis, where the full line represents the 1 in 15 case, and the dashed line represents the 1 in 25. We can see that for the highest energy waves, in orange and in red, for the 1 in 15 slope, the shoreline erodes about 1 meter, while in 1 in 25 the shoreline only retreated about half of the 1 in 15 case. However, if we look into the shoreline recovery during the lowest energy accretive wave, in blue, we can see that the beach recovery was higher for the 1 in 25 case than for the 1 in 15. In 1 in 15, there were barely any beach recovery, with the shoreline maintaining approximately the same location as when the accretive wave started, while in 1 in 25, the shoreline recovered up to the initial shoreline position of the second highest wave energy. Here we can see the bulk sediment transport of the irregular series, represented by Q in the y-axis. The bulk sediment transport is the sum of the sand transport rates of a profile in which positive Q indicates shoreward sand movement and negative indicates offshore movement. We can see that while for 1 in 15 the sediment transported during erosive high energy waves is more than double than in 1 in 25, the sediment transported during accretive wave is higher for the gentler slope than for the steeper slope. In this table, we can see the observations for erosive and accretive waves for the 1 in 15 and 1 in 25 beach slopes summarized. For the erosive wave, we observed a higher main bar growth and migration, shoreline erosion, and sediment transport for the steeper slope in comparison with the more gentle slope. As you may know, the morphology influences the degree of wave dissipation along the beach. Such differences in bar migration and growth can be directly correlated to the dissipation of that same energy, since the waves in 1 in 25 were breaking along a wider area starting on a more offshore location than in the steeper slope. Under these conditions, the wave energy is transferred continuously from short waves frequencies to infragravity waves, being these ones predominant near the shoreline. This can also explain the higher sediment transport for the steeper slope than for the gentle slope, as waves break closer to the shore, bringing more energy to the beach. Besides, energetic surfs can possibly increase the amount of sediment advected from the surf to the swash. However, it is still very poorly known the contribution of the advected sediment on the sediment transport in the swash. Also, another process involved in the sediment transport related to high energy waves is the existence and thickness of the sheet flow layer. The higher the energy is, the more likely it is to have an important and thick sheet flow layer, which significantly contribute for sediment transport. Although we know it has an important role on the sediment transport, we don't really know yet the overall major differences between its thickness and influence on the transport when the same energy is applied in different slopes. For the accretive wave, the shoreline recovery in 1 in 25 was seen larger than in 1 in 15. Even when in both cases a berm was generated and the erosion of the outer swash increased. This could be correlated to the total amount of energy arriving to the shoreline and the degree and predominant type of wave-swash interactions at the outer swash that may vary within the two different cases. These are just a few of the processes that may be directly influencing the differences we see between the two slopes. Further investigation is in course using the obtained new experimental data to examine these differences in detail at an intra-swash scale, where we will approach the process mentioned before. Thank you for your attention.